Hello guys, welcome to this last video about combinatorial analysis. This video is about combinations, the last tool that we need to study in this section. So of course, let's recall the definition. The number of combinations of n objects taking r at a time is just written with this symbol. Of course, you can also find it like this in your calculators, and you can think about it as the number of subsets of different subsets that we can make, subsets of size r from an original set of size n. Remember, always the population first and then the sample. So warning again, this represents a combination, and this is never the same as a fraction. I know you must be bored with this, but semester after semester my students keep making this mistake, so that's why I make so much emphasis on this. So please never equate these two expressions. They are not the same. Remember, combinations, in combinations, order is not important. Remember, associate combinations with subsets. So as I said, this is the same as this, so combinations, consider this the same as this. So please, order is not important in combinations. So example, consider the Florida lottery, or any lottery. I believe they behave all in the same way. So in the Florida lottery, they select 6 integers from a group of 53 to tell who is the winner, the weekly winner. So if we don't care about the order, in how many ways we can select 6 out of 53 integers? Well, of course, the answer is given in the ways of combinations. 53 combinations with 6. Let me do that computation. 53 combinations 6, and that gives us almost 23 million. 480. Let's round it up to 23 million. So we have 23 million different outcomes, different possible outcomes. So of course, if you buy just one ticket, the probability of winning is 1 over 23 million. Let's do it. It's something around 4.35 times 10 to the minus 8. So that's a very low probability. So if you want to get rich, find another way. Do not play the lottery. Another example, a poker hand consists of 5 cards. And those 5 cards are drawn from a playing deck of cards of 52. So how many different poker hands are possible? Of course, again, we use combinations. 52 combinations 5. Let me do that very quickly. 52C5, and that is 2598960. So that's 2.5 million different poker hands. So why do we compute this with combinations and not with permutations? Because let's say that we have some 2 and some 5 and some 2 and a 7 and an 8. Well, that's the same poker hand as 2, 2, 5, 7, 8. Sorry, I missed a comma here. And it doesn't matter the order. You still have the same cards. You still have only a pair. So that's why we compute these with combinations. Last example. If we have a group of 12 students and we need to select 5 of them for a field trip, how many groups of 5 can we make? Well, again, combinations. 12C5, so let me compute it, and we have 792. And again, this is a very simple computation, this is a very simple procedure, but again, I believe that in this type of examples, 12 and 5, these are not very big numbers, but just as subsets, we can have almost 800 different subsets. I believe that's very counterintuitive. Just as with permutations, combinations are very powerful. They save us a lot of time and they make our life very easy. So that's it. I hope that you're getting the hang of this. So whenever you're faced with a problem like this, ask yourselves, is order important? Is order not important? So you can realize if we need to count using combinations or permutations. So thank you guys, see you next time.